Alright, we got a lot of board to cover here. So, in our previous video we talked about an introduction to the idea of trigonometric functions with sine and cosine with arbitrary powers. Now we want to kind of nail that down for specific cases. What is the methodology for solving an arbitrary case where I have sine to a power and cosine to a power dx? Now for our purposes and what we're doing now, we want to only consider the cases where m and n are both integers and those integers are non-negative. So we're not going to consider the case where either one of these is like -2 or -5 or even +1/2 or anything like that. That's not what we're trying to do right now. Though there are some interesting things we can do if those cases come up. But since these are integers and they're non-negative, we can really just sort them into two categories. They're either going to be an odd integer or an even integer. And again, remember that 0, if one of those is 0, that's a case where it's actually even, because even numbers is anything where you can actually divide it by 2, and odd numbers are you could divide it by 2 if you added a number to it, right? So like if I have 11, I know that if I add 1 to 11, I can divide it by 2. Versus 0, I know I can divide it by 2 directly. 0 divided by 2 is 0. So anyway, that being said, we're going to sort these into 4 different categories, right? So I have two numbers. They could either be even or odd. So I have 2 choices for the first letter, and I have 2 choices for the second letter. That gives me 2 times 2, or 4 choices, or 4 possible permutations here. The first case we'll consider, which is actually the easiest, which is if this number is odd and the other one is even. So an example of that might be like sine cubed of x times cosine squared dx. Since this number is odd, what we're going to do is instead of writing it just as m, we're going to rewrite it. We're going to say that it's equal to 2 times some number plus 1. So if you're having trouble with that, do yourself pause, consider the fact of why is it true that every odd number can be represented as 2 times some number plus 1. Just think about that for a moment, right? You could subtract 1 from it, and that would make it even, which means it's divisible by 2. So if you divide it by 2, that tells you what k would be. So, for instance, in the case where this would be like m was 7, then m is 7, k is 3, so I have 2 times 3 plus 1. So anyway, that's just a little bit of elementary number theory for you. So what we're going to do is we're going to rewrite this. We're going to split the odd case. We're going to split one of them off. We're going to put it right here. And then the rest of them, sine of 2k, sine to the 2k power x times cosine to the n dx. So really all we're doing is we're splitting off one of the sines and leaving the rest of it alone. Then what we're going to do is we're going to convert each sine squared term to 1 minus cosine squared. So what does that mean? Well, if it's sine to the 2k power, well, that's sine squared times sine squared times sine squared k times. Again, in the case where k is 7, or where m is 7, k was 3, so that would be sine to the 6th x, which is sine squared times sine squared, right? So that's 3, that k times. Split that out here. And then what I'm going to do is I'm going to take that value and I'm going to rewrite it, each one of those sine squareds as 1 minus cosine squared. Remember, that's the Pythagorean identity. So boom, boom, boom. So the same thing here just becomes 1 minus cosine squared. And the reason I'm doing that is I'm setting myself up for a U-substitution. I can say, okay, well I have a bunch of cosines here, but I only have a single sine. Well, I know that if I take u to be cosine of x, the du is negative sine of x dx. So what that does is that kind of absorbs that dangling sine. That absorbs this dangling sine dx. Converts it to a negative, right? Because we get a negative from that substitution. And then I have those 1 minus, instead of 1 minus cosine squareds, there are a bunch of 1 minus u squareds. And then I have u to the n du. Now, there is something, just gonna to put this out here, which is that if you have like a minus, or a, you can do a minus b to the k. There is something called binomial expansion, which is what this really is. This is 1 minus u squared to the k. So you could look that up if you want to, the idea of a binomial expansion. It gives you a generalized formula of how to take something that looks like this and spit out exactly what happens when you multiply it out. If you've only got like 3 or 4 of those, it's not that, I mean, it may be useful, but it can be kind of complicated, and if you're not familiar with the idea of combinations, permutations, that sort of formula, it may not be worth your time. But obviously, if this was like to the 100th power, you're going to have to use something more powerful because you don't have the time. So anyway, just a little extra piece there in case you wanted to look something like that up. Finally, once you're here though, it's in polynomial form. Maybe ugly, but it's polynomial. So you can solve that. Polynomials are fairly simple. You just multiply it out and apply the power rule, and then don't forget to convert back to x's. Okay, so I know that's kind of rough because I told you that was an easy case, and it is. But luckily our next 2 cases are also fairly easy. So the next case is that m is even but n is odd. So in this case it might be sine squared and cosine to the 5th. Okay, in that particular case what you're going to do is you're going to follow this exact plan. But instead of splitting off of a sine, you're going to split off a cosine. And instead of a bunch of sine squareds, you're going to have a bunch of cosine squareds. And then a bunch of 1 minus cosine squareds, you're going to have a bunch of 1 minus sine squareds. And then same on. So it's really the exact same process. Just the only difference is, instead of doing this with, you treat sines one way and leave cosine alone, in the other case, you're going to split cosine and mess with it and leave the sine alone. The only difference is, remember that your when you pick your u to be sine of x, your du is cosine of x dx, not negative cosine of x dx, right? That's just standard calculus. So just remember that. They're really the same formula. So I'm not going to waste your time and go through that. The third one is actually your ideal case. It's that m is odd and n is odd. So if I had like sine cubed and cosine cubed, then I can actually pick either one. It doesn't matter. Because what you notice over here is when we walk through it, that cosine to the n, it actually didn't matter what n was, right? We never needed to use anything about the fact that n was even or odd. It just sort of dangles to the end here. It doesn't do anything. So in the case where both of them are odd, then you just take your pick. If you like doing it with splitting off a sine, great. If you like splitting off a cosine, great. Just live your life. You'll get the same answer. It may not look exactly the same, but I guarantee you it is equivalent. So finally, we have the worst case, as I note here, which is that both of them are even. Now again, remember that is also including the case where maybe n is 0 or maybe m is 0. So if you just have a singular integral like cosine to the 8th dx, or cosine to the 8th x dx, that is the case where they're both even. So then to do this, we're going to have to be a little more clever. What we're going to do is we're going to say, okay, well, then I know that both of those numbers are divisible by 2. So I can represent them as 2 times something. So again, if you had like sine to the 14th, or sine of x to the 14th, then that's really sine of the 2 times 7. So in that case, k would be 7, or something like that. Why am I doing this? Well, it'll hopefully become obvious in a second. So I'm going to take this, and I'm going to rewrite that as 2 times a number, 2 times a number. So I'm not doing anything other than just rewriting those numbers. Then, by the law of powers, right? Remember that if I have 2 powers multiplied together, I can kind of write it as like a power to a power. Think like x to the 6th. That's the same as saying x cubed squared. So because of that, you can x cubed quantity squared, not x cubed squared. That would actually be x to the 9th. Anyway, we rewrite this as sine squared to the k, cosine squared to the p dx. Ugh, right? By doing that, then we can exploit the half angle identity, which is not the most fun of identities. And that's that sine squared x is 1 minus cosine 2x over 2, and cosine squared x is 1 plus cosine 2x over 2. So they're really close, just one is a 1 minus and one is a 1 plus. So in doing that, we can take So notice we have a sine squared and we have a cosine squared. So we're going to replace any sine squareds with this quantity, any cosine squareds with that quantity. By doing that, we go from here, where that's where we're at, and replace it with these. Now, one thing that I like to do when I work these problems is those 1/2s really get in the way. So what I can do is I can pull out a 1/2 and I can pull out a 1/2, but I have to pull them out to the powers. So I have to pull it out as 1/2 to the k, 1/2 to the p, 1/2 to the k, 1/2 to the p, which then becomes 1/2 to the k plus p, right? That's how powers add. 1/2 to something times 1/2 to something. When you multiply it together, it's 1/2 to the power plus power. And 1/2 to the k plus p is the same as 1/2 to the k plus p. So that leaves us with this, which is slightly less ugly. But here's the thing. At this point, you got to multiply it out. So there are some other things you can do to reduce to make your life a little easier, but I don't want to complicate things by going into that. You got to multiply these things out. So if this is like a 3 and this is a 5, you've got to multiply that out. It is disgusting, right? Because it's just polynomial after polynomial after polynomial, just throwing out everywhere. But it's polynomials involving sines and cosines. Or really just cosines. So you got to multiply it out. Now, what you're going to find once you multiply everything out, do your distributive property or FOIL method or whatever you have to do, that you might end up with like a cosine. If you do this, even if these were 1 and 1, you'd end up with like a cosine squared 2x. Well, that's no good because I need everything to be in terms of odd powers. So if I have a cosine squared 2x, I actually have to take that and convert that to 1 plus cosine 4x over 2 so that I can get an odd power. So hopefully what you're noticing here is that the goal of what we're trying to do is always get back to odd powers, because odd powers are straightforward. We can use the standard substitutions. Even powers are not straightforward. They have to use these half angle identities, which make them kind of disgusting. So you have to keep going, and then if you end up with like a cosine squared 4x, which might happen, you might have to convert that to 1 plus cosine 8x over 2. And if that's 8x, that becomes 16x, and so on and so forth. And so you kind of end up with these increasingly large and less fun quantities. Nonetheless, it's just par for the course sometimes. You just have to do it. So once you're finally there, use U-Substitution as needed. You may not need to, but often you do. And then solve. And again, we're out of board space here. We're going to work some examples to kind of show this. But these can take a lot. Like a problem like this, a lot of times, is a whole board in and of itself. And that's me knowing how to do it. You not knowing how to do it, ugh, good luck. So it's an important skill. It's good to learn, but these are things that are going to require time, effort. They don't usually come naturally. They're not just oh, I get it now. You have to kind of work at it. But once you do, it's pretty hard to forget.